linear model. Here now we have proposed various image set models, but the interframe modeling does not necessarily mean temporal modeling. A local cue of temporal dynamics is motion. The spatial global motion can be estimated using robot future matching. The spatial local motion, here we basically mean the moving objects in the scene can be modeled by detection and tracking. Now the task is not just to recognize but also localize the action. We call the online boosting-based tracking method, which is shown in the top figure for tracking of face. It's appearance-based and does suffer from the drifting problem. When the tracking results is inaccurate, then the chosen updated samples, positive samples, will be also inaccurate. As a result, the induced updated classifier is going to be less and less discriminated. This is also called drifting in the context of tracking. Then we need to, there's something called multiple instance learning was introduced to address this drifting problem. Basically, we no longer claim a certain sample is for sure a positive sample. We can choose a set of samples around the candidate locations and then hope some of them are the real positive samples. This is called multiple instance learning, was introduced to address drifting problem. Also we call the Bayesian filtering based tracking method, based data association method. Basically it makes prediction based on the posterior motion state transition probability. Can the Bayesian filtering can also be introduced to address this set of drifting problems? Probably yes. We can equate the particle in particle filter with the samples in multiple instance boosting. So we propose a new algorithm called MILPF for tracking. The multiple instance learning response now will be weighted by the likelihood output by the particle filtering. We tested again on the Born benchmark of tracking forward. The evaluation metric is a single location error score of the overlap between the ground truth and the prediction, and also the overall precision, which controls the ratio of the successfully tracked frame number over the threshold of overlap score. Here is the performance for one sequence in the forward data set. The top row shows the overlap score. The second row shows the overall precision. The first column shows the tracking results, the tracking evaluation results for when the scale is fixed. The second column shows for the case when the scale is adaptive. We also tested on the Stanford YouTube data set. The overall average precision is 0.84, which improves the baseline MIL track. Basically, we just introduced particle filtering into MIL track, improved MIL track by 30%. It performs even better than the TLD, which is a powerful tracker, which is called tracking learning detection. Taking one video as an example, here shows the tracked bounding box. I don't think you can see the bounding box, even I cannot see it, but don't worry. Here's the detailed evaluation for that sequence. The single location error is the blue curve, which is stably among one of the lowest, specifically for this sequence. The overlap score is among one of the highest. And more importantly, this is the overall precision. When we choose the threshold of the overlap score to be 30%, which is quite low, our method still performs the best. If we require a more accurate tracker, then the threshold bar needs to move towards the right. Then the performance over the second best is becoming even larger. In summary, the proposed MILPF tracking algorithm induces a good balance, good compromise between appearance similarity and motion consistency. One is given by MIL boosting, the other is given by the Bayesian filtering, particle filtering based motion model. It achieves the best for overall performance, a huge boost over the baseline MIL tracking algorithm, and it's even better than the powerful TLD. Till now, the local temporal model combines appearance and motion cues still in the result level. Once we generate the sample or the particle, we want which each other is combined in the result level. Can we combine them in the future level? Yes. A spatiotemporal model treats a video as a 3D graph. Then the generated future will be a spatiotemporal representation, hopefully. Namely, time is treated as another dimension in space. This assumption holds under a set of settings such as locality and being semantically meaningful. Let's take a look at two examples. The first one. Now the task is segmenting the object, the action, or namely the moving object. Although it's shown for human, we want to design a generic model that is independent of object class. With a robust tracker, we aim to segment that object locally. One way to segment an object locally is to train the image as a set of pixel graph and then apply graph path. For a local clip, it can be modeled as a 3D graph as shown in this figure. The pixels forms a 3D graph. The observation is the pixel value z. The latent variable q basically denotes whether that pixel belongs to the object or not. We want to find a cut that minimizes the energy, the graph energy, consisting of the data term and smoothness term. But it needs to start somewhere, right? In the interactive portion of graph cast, the user manually labeled the seeds, so the graph cast starts from the seeds. But in our case, the seeds can be learned or estimated from the shape price that is learned online. As shown in the top of the figure, these local patches are retrieved from the label me dataset according to the similarity with the test input objects. The label me dataset provides 1 million images, annotated images with rich categories from the word net. But normally the shape needs a high order polynomial to represent. Namely, the corresponding silhouettes are highly nonlinear. As a result, we project them into the high-dimensional space using kernels, and then run PCA in the kernel space, which is also called the kernel PCA. First, we want to add a shape energy term, S, derived from the reconstruction error. Basically, this is the pre-image, this is the projection. The derivation is non-trivial, so as it's hard to enforce kernel PCA, but it involves an approximation method to do so. Second, we double use the shape priors as the posterior probability. As shown in this, we no longer use the probability z given q, we use the posterior because we have the shape prior. What about the likelihood? The likelihood basically is estimated from the image itself by Gaussian mixture modeling. Now the graph energy, and namely the objective function, is ready. We visualize how we learn the seed labels consists of seed label constraints to complement the optimization problem. Giving a test input, we retrieve similar objects and learn a shape prior that is called occurrence frequency map, or FM. Imagine we don't have the prior knowledge that this object is a person. Then this shape prior gonna be this shape prior gonna be enough to distinguish this object against a car animal. Then the posterior probability map (PBM) is learned once we have the shape prior and the image likelihood estimated. For PBM, we estimate the initial seeds that will be used for graph cast. We also have a strategy to update these seeds over time. In summary, once the seed labels over time are generated, the max flow mean cut algorithm will be used to segment the object. In the interest of time, I won't elaborate too much. Now look at the experiments. We tested again on the sample, the YouTube dataset, and we make use of the tracking results. In our method, there are 3 top-down constraints: the rough location, the shape priors, and the seed labels. There are 5 variations in total. The function without tracking but with seed updating does not exist. A higher precision basically means less distraction, namely fewer outliers and fewer false positives. A higher recall implies a more complete segment, namely fewer false negatives. Here are a set of comparisons. Basically, the information is here. The tracking and seed label update both induce less distraction, and the shape energy term induce a more complete segment. We can take a detailed look when we get to Q&A. Here are more results. Our method is evaluated on the whole YouTube dataset. Our overall F score is better than the previous state-of-the-art method that is specific to segment human bodies. As you can see, our method can segment cars and planes as well, as long as the label me dataset contains that category. Instead, the previous state-of-the-art method, their training samples are manually prepared. Here are more results for segmenting people doing running, dancing, playing football, playing tennis, and so on. Basically, this data set, they don't Stanford group, they extend this data set to a larger, even larger data set, which is called sports 1 million nowadays. In summary, back to 2012, this proposed model is the first time to extend the seed label to the temporal domain to estimate the seed over time. It is verified the tracking and seed label update induce less distraction, while the shape energy term induce complete segments. And also segmenting object locally makes the pixel graph representation work effectively, and it is also possible to assign shape price locally in the local 3D patch, 3D cube. Now let's look at a second example of a 3D graph representation to generate spatiotemporal features. Recall when we talk about the image set models, we went from the recognition of facial expression to the assessment of pain, a specific category of facial expression. Could we extend this to human actions? Probably yes. Let's see how we regress a diving score through a so-called pseudo 3D, P3D network. It needs huge memory and training data to train 3D CNN directly, like this. Instead, and intuitively as 3D convolution kernels can be separable, 3D CNN can be trained in the way of fine-tuning 2D CNN with an extra 1D CNN. That's the basic idea of P3D. If the 1D CNN is performed separately, then basically it's the same idea with Colin's TCN. P3D is trained on the large-scale kinematics dataset. We want to make use of this pre-trained P3D model. However, it only takes inputs of 16 frames, as it's trained in that way. Our solution is to score it stage by stage. It's fine to sample 16 frames within one stage, as long as the sampled frames are able to capture that stage. The platform diving action has a strict sub-action template consisting of preparations, jumping, dropping, entering into water, and finally the camera will capture the pool, the water spray. We can use TCN to segment the full video into stages, train P3D on each stage, and finally use a fully connected layer as linear regression. While scoring stage by stage is intuitive, it is the first time to score them stage by stage in the sports scoring literature. For example, reference 4 runs supported regular regression on their MIT dataset. Basically, they run SVR on their keyframes, human poses, and skeletons, and then do regression. Reference 2 builds a new dataset based on the MIT diving. They call it a UNLV dive. They apply C3D convolution 3D. Basically, it's a parent version. It's real 3D convolution. It's a parent version of P3D. They apply the C3D on every 16 frame clip, and then apply STM on the C3D features. It turns out the performance is even worse than simply applying SVR on C3D features. Probably the reason is that STM does not work well because the clips do not necessarily contain a semantically meaningful cliff, or semantically or temporally meaningful subaction. Now let's look at the performance on our performance on a new data set. Similarly with pair regression, the evaluation metric is the correlation. Differently now, one video only has a single label. So we use the Spearman rank correlation. Our best performance is 0.86. We better than the previous state-of-the-art 0.74. You may notice that this bottom values don't have standard deviation because it's linear regression or concatenation of features. There's no randomness. The temporal subcombination is pretty accurate. This is for the people who use TCN in their daily research. Let's take a look at the boundary frames. 0 is the start, 50 is about to jump. We predict 52. 65 is about to drop. We predict 62. Basically, the prediction are very close to the ground truth. The total accuracy is over 96%, but even better than ASTM. For those who may not know, TCN is a CNN inputted with 1D time series features, and the TCN is just the autoencoder portion of TCN. In summary, the proposed segment-based CNN is the first time to score mapping actions stage by stage in the literature. The temporal segmentation performs well, giving a temporal template and can be embedded into the P3D framework through extra efforts. At this point, I have reached the end of my talk. Let me draw a conclusion from the aspects what you may learn from this dissertation talk, what has been contributed to the field to the area of video representation learning, and what can be done in the future. The primary takeaway of this dissertation can be categorized as follows. Basically, image set models can capture facial actions that are about collective representation. Sparse and low-rank models can have the expression identity and the pose cues untangled, and can be learned via an image set models and also a linear model. From these deep-based models, we can see that norm, if you remember in the very beginning, norm is related with recognizability, and the similarity matrix and the loss function both matter. Temporal motion models combining the MIL and the particle filter induce a good trade-off between similarity of appearance and the consistency of motion. Moreover, spatial temporal models work locally in both space and time to represent video as 3D graph, and work effectively when 3D CNN are inputted with temporally meaningful, not hard segmented 16 frame, but temporally meaningful clips. Lastly, segmenting object locally makes it amenable to assign shape price, and it is also possible, as I showed, to learn such shapes by such prior knowledge from the rich web data under wave supervision. I hope my dissertation more or less sorts the area of video representation learning, image set models, temporal models, local, global, and spatial temporal models. We propose a set of such models to recognize, localize, and assess actions, such as image set models. This is more like emphasis. We mentioned this in the very beginning. Image set models by aggregating subset features given by regularizing normalized CNN. Image set models by in the frame principal recovery and sparse coding residual actions. Temporal model estimated by action detection. Spatial temporal models with actions segmented by 3D graph class and quantified using 3D CNN. I wish the proposed models will lead to working components in building real-world face and gesture recognition systems. I hope this dissertation motivates further thoughts regarding how to use the structure of data, structure of video, and the requirement of task to improve the video representation learning process. As long as these thoughts continue to afflict us in the days and the years to come, I do believe this dissertation has achieved no small thing. Future challenges. The video data sets are getting larger and larger. For example, the recent video data sets, such as MegaFace, video data set, this is Google's FaceNet run on MegaFace data set. As you can see, when there's only one key, but for a lot of methods, even one key distractor basically means you are testing a face which does not belong to the training set. that's an extra phase. You can still recognize under post changes. With 1K distractors, Google's FaceNet is still robust. However, this mega phase dataset now provides 1 million distractors, which is very close to the real-world settings. Basically, when you get to airport, you don't just want the surveillance system to only recognize the person who has already registered. If there's a person who is the first time to that specific airport, you still want the face recognition system to recognize it. But if we increase to 1 million, even Google's FaceNet transform tons of data dramatically fails. So how to scale up these methods in terms of huge testing scale? Another example is for human action or generic video classification. Nowadays, the scale has been increased to over 1,000 categories and over 1 million images. And moreover, last year, since Alan's field, I helped Alan's lab to run a challenge, which is to do multitask networks. Actually, to be honest, there are 10 tasks. Every single task the datasets have been either created or published. But it's the first time to push the research of multitask. Basically, one network can do all the jobs. I would imagine in the future, can this happen to the video domain as well? So recently, Berkeley released this data set called BDD. For self-driving scenarios, basically you can imagine either the lane segmentation or the pedestrian detection, the object recognition. There are multiple tasks, but it's the same data source. Can we generate a multitask network which considers all the tasks? Actually, this is, to my sense, is the real self-driving data set. It's collected from a real self-driving cars, unlike a lot of benchmarks, which claim to be autonomous driving data set, but they are collected by human driving cars. Here are more references and the models that are not presented in the interest of time. Before I finish, I'd like to thank my wonderful mentors and collaborators. Now I realize that every decently cited paper from me is a collaborative work. Thank my committee members, lab mates, and everyone for attending. My dad flight from China over the weekend. He's sitting in the back. My wife and daughter are also, my daughter basically is crying, so maybe she's out near this room. They are also here to support me. I'm excited to hear some exciting questions, tough questions, philosophical questions. I will try my best to answer them. You guys have been a great audience so far, so let's keep it going. Thank you.